All right, so today is Hawaiian pronunciation. Um, I'm just going to keep those due dates as they are, even though those are rather far off. Technically, if I were to be doing it, would be due this week, but honestly, I think you all are under rather a lot of pressure at the moment, right? In all your other classes, yeah? So might as well just keep those due dates loose, but get those turned in. So I'm going to keep them in rather than trying to drag them forward and stressing you out more. So tonight I hope to also go through my calendar to make sure of lectures to make sure I can figure out when proposal day will be. I'll be starting. I think starting next week I'll be starting to talk about the final project and the ideas for it. But the idea here is that you'll have a pre-proposal lab during Lab 10, and then what will happen is that we'll have something called Proposal Day. On Proposal Day, we'll hold that completely over Zoom, because essentially what's going to happen is that I'm going to meet with every group over the course of the lecture and possibly after it, just simply to talk and check off that your idea is okay, because mainly I'm looking to make sure that you aren't trying to. I'm trying to look at both. You aren't trying to bite off more than you can chew, as well as trying not to propose too easy of a project. Students who are not really sure will often they'll say, oh yeah, we're going to do hangman, or we're going to do tic-tac-toe. And to each of those I say, no, those are too easy. Those are basic homeworks that we give. Instead, you will try doing this for hangman. Maybe you need to add a graphical component to it, right? Work with graphics. Or for tic-tac-toe, I'm going to say, actually, there's this awesome game made for kids called Goblet Gobblers. It's $15 on Amazon, but you can check out the rules online. And it's basically tic-tac-toe, but you can cover up other people's pieces, which adds a whole layer of complexity. It makes it actually challenging. So I'll meet with everybody. I'll be meeting people throughout that proposal lecture. And when I okay your group's project, you're free to go. So that doesn't make sense to bring everybody in that day. It makes more sense that we just hop on Zoom. The people who have a class at 3:20 following or 3:30 following this class, they'll meet first with me and I'll check them off. And the people who can stay later, you can just look at cat gifs or something while you wait your turn. So the idea here though is that I want to make it as painless as possible for everybody and make it, and it doesn't really, it's not, I don't want to have to waste anybody's time by making you come in here just so you meet with me for 3 minutes and then leave. So Zoom is one of the kind of ways that makes sense. And I'll be sending out an announcement when I nail down its date. Generally, I try to do it a month before the due date, the due date of the final project, which is the last day of class. So you get a full month to kind of, here's our brainstorm now, and let's go and slowly work on this. All right. So the Hawaiian word pronunciation lab. Geez, I am stumbling over my words right now. Okay. So this lab. As you may have seen some conversation on Discord, it's not so much that you cannot or are not allowed to use methods like replace or come on, I don't need this. Oh, there we go. It's not that you aren't allowed to use methods like replace or index or find. It's that they will actively harm you and work against you in this lab. Using the dot replace, because using the dot replace to say, I'm going to replace all the A's with an ah sound, that's going to be fine. But when you start getting into this, where you say, I'm going to replace, next I'm going to take the E's, and I'm going to replace every, E with the eh sound, okay? But then, so your string will be full of ehs now. But then when you go and say, I'm going to replace the I's, that can cause more E's in there. Because really bad if you start replacing the I's, if you do the I first, and then start replacing it with the E's. Also, It's fine for the single vowels, but once you start getting to the double vowels, that's when it starts really getting where basically you're replacing the pronunciations of various pronunciations with other pronunciations. And so you're ending up with, rather than like something like K key, you're getting a KE key instead. All right, so you can't really use the string methods for this one. What we do need to do is that we need to build we need to basically build our pronunciation string from scratch. But before we get into that, let's actually remind you what this lab is. Given a Hawaiian word, give me the valid, check if it's valid, and if it's valid, give me the pronunciation of it. Also, we want to loop this, but that can be added in. Let's just get it focus on writing methods that will get this working. So what does that mean? We want that there was two tasks, big tasks in there. Capital B, big tasks. Big task number one, which honestly is actually the medium to small size task, is to validate whether a word is a valid Hawaiian word. So I'm going to make that its own method. I'm going to go and say def validate, okay? And this will tell me true or false, is this a valid Hawaiian word, okay? Now, every other part of the program, the other parts of the program, and most importantly, the pronunciation is going to assume that validate works. For right now, because I need a placeholder for it, rather than putting in pass, I'm going to just simply say, yep, every word, it's a valid Hawaiian word. Okay, that's every word is now a valid Hawaiian word. Obviously, that's incorrect, right? But we can fill this in, okay? I always like to put something in as kind of just something that runs, even if it doesn't work correctly, right? It will run, it will work, it won't crash the program, but it will give me something, right? Next, the other big task is check if a word is valid and give me the pronunciation. So we're going to do a pronounce method. Def pronounce, given a word, give me the pronunciation of this word. Okay? Let's see, pronounce. Let's see. Let's give it maybe something like sound. The way the word sounds, right? That way we don't have to write pronunciation or whatnot like that, like 10 different times. And it sounds a bit better than putting P, right? So here what we're going to do is that we're going to sound out we're going to give the way the word sounds, okay? We're going to figure that out, we're going to store it in sound, and we're going to return sound, right? Does this work? No, of course not. It doesn't work right now. But it's going to run, right? This allows you to figure if you wanted to build your loop first, this would let you build your loop. I don't like building the loop first. I like to get these methods working, and I like to put them in I just used some Java terminology there, methods. So in Java, if you take 1068 next semester, functions will be called methods because that's the way it works in object-oriented lingo. Methods, functions, subroutines, subprograms, they're all the words for the same thing with slight subtle differences. There's pedantically, technically correct definitions between them that are important to some people. But for 95% of people, if you say function or method, people are going to go, yep. They understand you're talking about a verb, okay? The difference is who's performing that verb. So pronounce, validate, pronounce. We've got two verbs here. We've got two functions, okay? So to validate the word, let's think about that. That's fairly straightforward. How do we know if something's a valid Hawaiian word? It's a valid Hawaiian word if it has one of the 12 valid characters, A, E, I, O, U, P, K, L, H, M, N, W. Hawaiian is made up of only those characters, plus we also sometimes use an apostrophe here, like humu humu nuku nuku apu a. to separate the two ahs there. Okay? So the apostrophe we can worry about later. We'll just simply note that it is a valid character. In fact, what I recommend you do is you just treat it like a consonant. So let's go ahead and look at these. So their consonants are fairly easy to understand, which is that given a consonant, it's going to sound, for PKHLMN, it's going to sound like the English version. P, k, l, right? The English versions of those. W is the only weird one because it can be a W or a V. It says, okay, if it's at the start of the word, it could be a W or a V, but we're going to do W. If it's a W after the letter A, it could be a W or a V, but we're going to do a W. So, in other words, you get to just ignore this one and ignore this one. Okay? A W after a U or an O. Great. It's a W. So the only kind of thing where we have to worry about a W being not a W is an I or an E. Again, that's going to be in pronounce's job. And I actually recommend that being the very, very, very last thing you work on in pronounce because it is such an edge case, right? Vowels are straightforward. You've got two kinds of vowels. You've got your single vowels and you've got your double vowels. Single vowels, if you've taken any Japanese, this should look very familiar to you. A is for a, E is e, as in egg. So a is not a. We don't do a. A single A is always pronounced ah. Got it? Similarly, a single E is always pronounced e, like egg. I, oddly enough, that's used for the E sound, for the long E sound. So I is B. So I is E, like in B. O is O is nice and easy to remember. O gives you O. Okay? And U gives you oo, like moo, okay? Or boo. I mean, it is the Halloween season. My kid wants to dress us up as Harry Potter characters. So that's what I'll be doing because you go with what the kid wants. At least he's reading. So there you go. At least he's reading. All right. So the double vowels, like any language, double vowels become a bit complicated. Okay, and we'll be covering this more in pronounce. This really doesn't have anything to do with validate, but I wanted to go through the relevant bits first, right? A and I together become I. A and I together become I. Why is that? Because they are two syllables that merge together. A and E. A, E, 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 I, I, I. That's how you get it. That's it. That's why it's I. Okay, because it is A and E together. If you pronounce those together and you mush them together, A and E becomes I-E. Same A and E, by the way, does the same thing. A and O becomes ow. A and U becomes ow. How and house, right? E and I is how we also get an A sound. EU, EU, IU for your U sound. So we just keep looking at, so these are just a bunch of different ones you're gonna have to go through. But the question is how? Don't worry, I'll show you, at least a bit. Or at least I'll get you started on it, okay? So let's go ahead and go with the validate, okay? And so to do validate, let's just review what our two functions are. For validate, we got to go through and we got to look at all of the letters in our word and say, okay, if one of these is not a valid letter, we're going to return false. Otherwise, we're going to return true. For a lot of these functions that do true or false, it's always easiest if you assume something and then try to disprove it. So here I'm going to assume that the word is good, return true, but as soon as I show that it's not good, I'm going to return false. Only one character has to be bad for it to be false. So that's what we'll do there. For pronounce, what I'll do is I will iterate through this word, okay, and I'm going to go through each syllable, and I'm going to figure out what they are. So the issue is, how do you go from each syllable? Because all I know how to do is character to character. And the answer is you can't go through each syllable, so you have to do character to character. So we're going to iterate over all the characters. Now, how do you do this? Well, if I hit a consonant, that's pretty easy. Okay? If I hit a consonant, that's super easy. I'm just going to simply output the consonant. If I hit a vowel, I'm going to output the vowel. But then we get into the double vowels, right? So here's the trick. The trick is that we can't iterate over our word using a for loop, because a for loop is always looking dead center at what you're looking at, whatever the vowel character is, and you're always moving to the next one. Instead, we have to look one ahead. We have to look at basically, if I hit a vowel, I have to check, wait, is the next character a vowel too? And if it is that a valid character? Or does that make a double vowel? That's not as hard as it seems if we use the right tool, which is a dictionary. Okay? And if we use the other right tool, which is not a for loop, but a while loop. Because we don't know because when we read a double vowel, we're going to want to move 2 characters ahead rather than 1. Let's go ahead and take a look. So what we want to do, okay, as the first kind of hint to you, and this will make sense in a bit, is that I'm going to go ahead and make some variables. So consonants is equal to, and I'm going to turn it into a list, which is all the consonants, right? So our consonants are P. Actually, let's go ahead and drag this from the document, copy that, paste that, and then we'll just go through and hit this key a bunch of times, right, to turn them into variables. And I'm recording this, so if you slip up or something, don't worry. It's going to be here in the recording for you to look over it. You can also, we're going to want to do W as well because that's a consonant. This is all going to be lowercase. Do we want to add the single quote as a consonant? Maybe. We'll figure that out later. Okay. Next, though, and the reason I have this as a list here because consonants, except for W, are always going to give me the consonant, right? If I see a P in the word, it's going to be a P in the pronunciation. It's 1-to-1. Make sense? If I see an L, it's going to be an L in the pronunciation. The only exception is W, which is going to be a W or a V, which is why I say handle that last. Now, for the other one, for vowels, we see a vowel, but we are going to give it a syllable, but we're going to give it a sound instead, right? So in this case, we are going to use a dictionary, where the key of a dictionary is the sound. Sorry, the key is the letter, and the vowel is the sound. So I'm only going to do a few here because I want you to do, because it's your assignment. So vowels. So dictionary like that, using the curly braces. And then we're going to go ahead and do A colon is That means this means saying, okay, what is this dictionary saying? It says the pronunciation of A by itself is an And then we would just simply fill it out with all the other ones. The pronunciations of I is the E sound, like that. Make sense? And you'd fill it out with the other 3. Okay. Now, what about this one? Well, there's one more, which is double vowels. And I have this one as a separate one, just simply to make your if statements and pronounce a bit easier. Okay? Okay. So, we're going to do, so what was one of those? It was W. So let's see. A and I. Okay, sounds like I. So A and I gives us I. A and O becomes ow. Now, you don't necessarily need to use a dictionary to do this assignment. It just becomes like a, 50-line monstrosity, if not more, without dictionaries. Whereas if you use a dictionary, it becomes, as we'll see, quite tame. Okay. So I gives us I, ow gives us ow. You can add the rest as you want later. Right now, this is kind of like, you know, just to get you started, so to speak. Okay. So for validate, what I would want to do is basically ask, you know, for each character, it's very simple. For each character in the word, check if the character is in consonants or vowels, right? If it's not a consonant or a vowel, it's not anything, right? It's got to be a consonant or a vowel, or technically, yeah, so then I'm going to say, or maybe depending on how you code, right? So for each character, you check if the character is a consonant or a vowel, or maybe a single quote, depending on how you decide to write your code, right? And then we say, if the character is in consonants. If the character is not in consonants or vowels, then it is an invalid character. So return correctly. And then what we're going to do over here is that for return true, I'm just going to write down assume true. Right? So we're just simply assuming that our thing is true. Right? So that's practically, and if you know, and if you've got it, you're like, oh yeah, this is very easy to translate into this code. Right? It's pronounce now. Sorry. I'll give you a second more to check on that while I rehydrate a bit. Okay, so this is not too, so the validate is not really so bad, right? And what you're going to do with validate is you're going to use a while loop around it and say, basically you're going to ask the user for user input, you're going to ask them for a valid Hawaiian word, and while validate is false, you tell them no, bad user, enter another one. Okay? So then what we're going to do is we are going to so that while loop will keep asking them until they finally get one. And when you finally get a good one, that's when you move to pronounce. So pronounce doesn't have to check if word is good or not. We can assume that word is good because we're going to run it through validate first, and we're going to assume that validate works, right? And if it doesn't work, well, validate we can always test validate on invalid words. Check that, and pronounce. Again, we can test that independently of validate. So we've got our sound. Okay? So, again, as I was mentioning, what a lot of us want to do in these kind of things is write a for loop. For, now you're not going to want to do this, so don't bother, don't bother writing this down. For each, in Word, and then get the pronunciation. But the issue is that we have to look ahead. We have to look one step, we have to look to the character immediately to our right. Like now let me explain that in a bit more detail why. Okay? What I have to do, the way my algorithm needs to work is like this. For K key, this word over here, it's going to work like this. I'm going to go through and I'm going to look at the first character. I'm going to look at K. Is it a vowel? No. Sorry. Is it a double vowel? No. Actually, I'm going to probably check if it's a double vowel first. That makes the most sense. Is it a double vowel? No. Is it a vowel? No. Is it a consonant? Yes, it is. Awesome. I'm going to put out what consonant it is. Okay. Next, let's go to the E. Okay, so EI, is that our double vowel? Yes, it is. So it's a double vowel. So we started at K, we looked at KE to see if that was a double vowel, then we looked at K to see if it's a vowel, then we looked at K to see if it's a consonant. It's a consonant, so we put it out. Next, and I'm showing you how this algorithm is going to work, even though I haven't written anything down for it, because I figure doing it this way is the best. Next step, we say, okay, we're on E. Is I a double vowel? Yes, it is. So that is A. EI is A. So, yeah, if you check your document, it's going to say EI is A. Right? EI sounds like A. So so we have an EI, so we're going to put A here. Okay? And then because I know because of the way syllables work, which is whenever I do this vowel soundy thing part, that's the end of a syllable, I'm going to put a dash here. So I put A and a dash here. Okay? Now, because I read this, because I read EI, what I don't want to do is go next to I. Because if I did, I would say, okay, is IK a double vowel? No, it's not. Is I a vowel? Yes, it is. And then I would incorrectly do this. Right? I don't want that to happen. This word is just K key. Two syllables, not KE key, which is 3 syllables. So K. Then we looked at EI. So instead what we're going to do is, because we did a double vowel, what we're going to do is that we are going to move not one index over, like we did over here. We started at K, moved one index over. Instead, we're going to move 2 indexes over to the next K. It's only ever going to be 1 or 2, because, why is that? Because we read 2 characters, so we're going to move 2 ahead. Here we read 1 character, so we move 1 ahead. So next I ask, is KI a double vowel? No, it is not. Is K a double vowel? Is K a single vowel? No, it's not. What about, is it a consonant? Yes, it is. Okay, because it's a single consonant, I move next to the next one, which is I. Is I to the end of the universe of double vowel? No, it is not. You might be asking, wait, do I have to check for out of bounds on this one? Not if you use slices. Remember, slices don't care whether or not you're going out of bounds or not. So, is I a double vowel? No. Is I a single vowel? Yes, it is. So we do an E, and then we put a dash. Oh, it looks like we're done. Okay, so because we're done, I'm just going to remove this single dash at the end, because I'm going to end up with 1 too many dashes at the end, fence posting problem, and just return K key. So it works like this. Rather than using a for loop, we're going to use a while loop. We're going to keep track of the index here with index is equal to 0, starting at your index 0. And you're going to say, while index is less than the length of the word. Make sense? Because the valid index is, so if the word is 5 letters long, that's going to say while index is less than 5, which is great because the valid characters are 0, 1, 2, 3, 4, 5. So 0, 1, 2, 3, 4, not 5. Okay. Then what we need to do here is basically do a bunch of if statements. Okay? So if the index is so basically what we want to ask here is if the letter at this index is a double vowel. Okay, or rather this one and the next one are double vowel, then we want to go and get the next character. So if, okay, word, and then because we're doing index, we do something like this. It's going to be a slice operation, and I'll leave that for you to figure out. It's going to be a slice operation. It's a fairly straightforward one, though. If the word is, so if that slice is in double vowels, in other words, if it's part of the keys, add it to sound, add the pronouncing to sound, and then here's what you need to do. Increase index by 2, because we read by 2 letters. Make sense? Elif, and then in this case, it's if the word is a single vowel, make sense? Otherwise, if it's in the consonants, and you could do it in the consonants or the vowels first, it doesn't really matter. They're elif, so they're all mutually exclusive. And then I guess I'll put an else for because that we shouldn't be hitting an else there, but hey, that's going to be useful for debugging to have something there. Let's see. Oh, and one more thing. Add a dash, right? So you do the sound and then you add a dash to the end, right? Because just to be able to separate the things. If you don't do that, you'll get this and you'll be like, oh, I'm missing a dash. I got to put that somewhere. And you put it there. And actually, this is most of the assignment right here. I actually debate every semester whether or not this is too much to give. And part of me does think it's a bit too much. But this is, it is a fairly straightforward assignment once you understand how this block of code works. Which is that you're using a while loop to iterate through. Here we're incrementing by 2. Here we're incrementing by 1 and by 1 as well. Okay? And then once we're done, we want to return the sound, right? There might be some cleaning we have to do with regards to W's, but that can be added later as an exception, right? Similarly, handling the apostrophe, figure out how to handle that, because typically what I will test on is, I'll test on K key, and I'll test on humu, nuku, pua, because it's not as hard to spell as that seems. It's just humu, nuku, so it's humu repeated twice, humu repeated, nuku repeated, humu, nuku, and then you've got apua, So it makes it fairly, so it's not as scary as it sounds. There's even a nice song, you should listen to it. So overall, this assignment is going to be fairly straightforward, and it tests you on using our consonants and the like. Now, so now to talk a bit more about dictionaries and just kind of how to build them from scratch and stuff like that. But let's see. How's everybody feeling about file reading? Do we need to go review that more, or are we ready to talk more about dictionaries? Because I can do both at the same time. It just depends on which example I'm going to do. Yes, no? No on file readings? You want more file reading? No? Okay. Okay. Let's move on to some statistics then. I know that sounds scary, but honestly, I don't know statistics. Let's see. So let's go ahead and get these Discord out of the way. Okay. So statistics can be hard at some point, and the entire point of the next block of our material is that don't do hard things then. Okay? What we're going to be talking about are something called Monte Carlo approximations, or Monte Carlo methods. Okay? And Monte Carlo, let's go ahead and open up a private window, not because it's anything, but because I don't want to drop my home address on the internet, that's all. It's useful for those kind of things. So Monte Carlo is very interesting. If you look where it is, it's in the country of Monaco, which is one of those weird things in Europe that you occasionally get, specifically microstates, right? Like Luxembourg and Liechtenstein. And the often left out of discussion, Andorra, I believe, right? If we just simply scroll out to over here, yep, Andorra, which sits right between Spain and France. Very nice places, I'm given to understand. It's just one of those nations that's just its own thing. Monaco is its own thing, and Monte Carlo is a small area inside a small area, which is home to a famous casino. Okay, and this is where Monte Carlo approximations get its name from. For those of you who don't know, statistics and probability sounds boring, but it actually has a very exciting, a very nice and exciting starting place, which is that is what mathematicians did kind of to make money, which is that they wrote guides on gambling or did calculations on probability for people who wanted to gamble. True story. If you want to know more about the history of randomness and the study of randomness, there's the book called The Drunkard's Walk. It's rather good. It talks about various things, such as false positives in tests, which happen, and why often you need to test twice on things that are rare because of what's called Bayesian probability, the probability of A given B. Okay? So now the idea comes from the fact that figuring out a game of roulette or whatnot, the probabilities of winning at that, we could calculate those by doing, the probability of where a ball lands, except maybe it's tilted or rigged in some way. The way you figure out the probabilities, then, in that case, is that you do observations. You literally observe to see, okay, what are the probabilities of me winning this game? Count the number of people who win and lose. Count the outcomes, essentially. And this is very useful if the probability is a bit too hard to figure out. I mean, this is what I did for part of my dissertation, which is I did a lot of simulations, effectively a Monte Carlo approximation. It sounds very complicated, but it's not. Also, because we don't necessarily know what the outcomes are going to be in advance, we use a dictionary to store them. Okay? So let's go ahead and talk about just kind of, Bernoulli numbers, right? Let's talk about a fancy term called Bernoulli numbers. Okay? Right, it says sequence of rational numbers frequently announced, Taylor series, hyperbolic. Honestly, though, it's named after, oh, wow, really? It goes that by far? Binomial coefficients. So basically, what this comes down to is that there's probabilities with coin tosses, all right? So suppose I challenge you to a game, okay? Fine, let's do it like this. Suppose I challenge you to a game, okay? It's like this. Simply put, if you can get, you're going to flip 10 coins, and if 5 of them end up heads and 5 of them end up tails, you'll win $1. But if that doesn't happen, I'll get $1. Right? And of course, it's completely fair after all. There's 5 coins. The probability of any coin landing on its head or tail is 50-50, right? So obviously, this entire thing the probability is going to be 50-50, right? No. This is, in the world of statistics, that's not how it works, right? But in the world of scamming, it sounds perfectly nice. The idea here is, right, if we flip 10 coins, what's the probability that 5 of them, and that we get 5 heads and 5 tails, right? Now, if you've studied statistics or probability, you know that the answer to calculate is to take 1/2 and raise that to the 10th power. But you haven't studied statistics. Most of you are fall freshmen, right? Who would probably be able to get to that right answer. But what if you don't want to do the statistics? What do? We simulate it. So the way the Monte Carlo approximations I like to teach them is I always create a method called the game method. Okay? And the game method, it will return whatever I need it to. It can be the result of a coin flip. It can be the result of the result of a coin flip. It can be the result of something, of anything, actually. It could be just simply who wins versus who loses, right? In this case, I'm going to return the probability of I'm going to return the outcome, okay? So what's the game here? The game here is I'm going to flip 10 coins, right? And we'll see what that gives us. So I'm going to put pass here for right now, because we do need to bring in something very important here, which is our import random function. Okay? Import random is going to be our star of the show, so to speak. It is what makes Monte Carlo approximations work. Now, as I mentioned previously in the semester, randomness is actually pseudo-random. Okay? What that means is that basically is that I can actually set it up so that it gives me the same results each time, which is useful in simulations. But most of the time it uses like the system time and a bunch of other stuff to generate random numbers. It's very powerful and very useful like that. And Python's random library is really good because it gives you the ability to do a lot of things. So what do I mean by that? Def flip. We're going to just simply write this method to do a coin flip. Now the coin flip works like this. Okay? What are the sides of a coin? Not the sods, the sides. Sides of a coin are as follows. I could do this as a list or I could do it as a string. I'm just simply going to do this as a list. Sorry, as a string. The sides of coins are heads and tails. I'm just going to use capital H and capital T for them, right? And it is very simple for us to simply do this, to figure out which one of these is random, which side is going to be random. I'm going to break it up into steps for us. Choice is equal to, I'm just trying to remember what to name it. We'll figure that out in a second. To choose one of these two things, what I use is a tool called random.choice. Okay? And this is what makes it so nice in Python. In Java, you have to actually do a few steps like, okay, how many items are there? I'm going to generate a random index, and that's going to be my number. Instead, this just simply says, hey, here's our collection. I'm going to use this. So what we're going to do is we are going to go ahead and just kind of show you how this works with the Python shell. All right, I'm going to open this up and say import random. And we are going to go ahead and I'm going to say sides, just like it did, is equal to heads or tails. And what we're going to do over here is we are going to do random dot choice tails, heads, tails, tails, tails. So as you can see, it's going to give me a random selection each time for one of those. And the reason it didn't print out anything there was because I was pasting too quickly, that's all. So, and notice, by the way, that we can get some things that don't necessarily look random. Randomness isn't always, quote unquote, even, unless you do it enough times, right? Means if we were to flip this 10,000 times, we'd have approximately close to 5,000 heads and close to 5,000 tails, but it wouldn't exactly match up. Okay? So what we're going to do here is, so this works. It would also work, by the way, if I instead did something like this. So if I were simulating a dice roll, right? For those of you who need to know that for Dungeons and Dragons or something. 1, 2, 3, 4, 5, 6, right? Or you could just simply create a range for that. Instead, sides is equal to this. Random.choice. Oh, I've still got that queued up in my clipboard. So 3, 2, 5, 4, 3, 6, right? Ooh, this is nice. We didn't really get, it took a while for us to get a 1. That's good. Okay, so see, it just simply selects something at random from a sequence, which makes it really nice. So going back to our challenge over here, we've got something that allows us to say, here's our flip, here's our sides, and we're just going to return random.choice sides. Right? We're going to return what we flip. So the game is to flip 10 coins, right? So our game is to flip 10 coins. So I'm going to say our sequence of flips, I'm going to say that seq is equal to an empty string. And we're going to do this 10 times, right? We want to do this on a sequence of 10. So for, I'm going to actually do this here, num flips. Because I'm also going to use this as an opportunity to teach you about default arguments, I hope. For I in range num flips, we're going to flip the coin 10 times. Sequence plus equals flip. In other words, give me a random coin flip. We're going to add it to our string, and that's it. And then rather than returning who won or lost, I'm just going to I'm going to leave that for later because I want the statistics on this. I'm going to return the sequence. Now what I'm going to do is I'm going to print game over here. I'm going to call the game and run it just so that we can see our outputs. Okay. Monty 1. Okay. Invalid syntax. What did I mess up? In range. Thank you. So we have head, 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 tail, tail, head, tail. Okay. If we run it again, we get tail, 3 heads, tail, head, head. Run again, head, tail, head, tail, head. Okay. Now, the easiest way to figure out, so I want to figure out actually what is the distribution of these things, right? How often do these things happen? Because we haven't gotten 5 heads and 5 tails yet. it's going to take us a bit if we try. That's not 5 heads and tails. Oh, there we go. Wait, no. 1, 2, 3, 4, 5, 6, 7. Oof. Nope. Nope. Right? We're looking for 5 and 5. That's what we need to win. Wow, we've forked over a lot of money so far. All right, there we go. Finally. That's the point of the game, though. It's a rigged game. So, right? So let's figure out what the statistics for this are. I'm going to go ahead and I'm going to create a dictionary called outcomes. Now, I don't know what the outcomes are going to be in advance necessarily. So, I'm just going to create an empty dictionary. Okay? And let's go ahead and actually make this a bit easier to read. What I'm going to do is I'm going to return sorted sequence instead of sequence. What does that mean? I'm going to return, well, that returns a list. So this gives us a list, but now you put all the heads and all the tails together, which lets us kind of visualize it a bit easier. But so that returned a list, though, and I'd rather keep it a string, so guess what I'm doing? Let's see, can I do that? No, I can't. What I need to do, right. Okay, can I do, give me 1 sec. I know how to do it, I just don't want to avoid using a join operation. Can I just do sort, like that? No, I can't. Darn, I was hoping to. Ugh, okay, fine, you win. Okay, sequence is equal to sorted sequence. I'm going to break it up so it doesn't look so ugly. This turns it into a list that's been sorted, right? All the heads followed by all the tails. That way we'll be able to visually see a bit easier how many there are. But I really want this to be a string, so I'm going to use I'm going to use the method that turns lists into strings, which is I'm going to, I think, .join, I believe. I hate doing this because it looks so messy, but it is the way to do it. Which says I want to use this, the empty string, to join all the elements in the sequence. Which now you'll see what that does. And it works. And now it's a lot easier to tell how many heads versus how many tails I've got, right? That sorted it. Now, why do I do it like this? Because I want to list my outcomes as I care about the combination, not the permutation. The combination being the technical term in statistics and probability for basically I care about the number of heads and number of tails. I don't care about the permutation, which is the order in which they appear. That's why I'm sorting them. I don't care about the order. 5 heads versus 5 tails doesn't matter where it happened, right? If I did 5 heads and 5 tails, 4 heads and 4 heads, 1 tail, 1 head, and the rest tails, right? It doesn't matter for probability's sake. It's the outcome I matter. Yes?
Well, I was going to ask is, so when you use seek equals sorted seek, is that returning like a list?
It is. It is returning a list, and that's why I do the join. Because by default, it takes in a sequence of something, which is a string or a list, and returns a list. So, and then I say, okay, but lists, I don't need this, so I don't need this bit. Okay, but if I don't have that line, what do I get instead? Same deal, it's just harder, it's just a bit harder to read, see? It's a bit more spread out. So that line gives me the ability to have it less spread out, a bit more concise. Okay. So now we need to, what we're going to do is we're going to simulate this game a bunch of times. Okay? So this is the main loop of this. For blank in, so here what I'm going to do is I'm going to put something called trials up here. Trials is equal to, let's do 1,000 games, right? We're just going to do 1,000 games. For blank in range trials, because I want to do this. Because again, I don't care about if it's game 1, game 2, game 3, game 4. It doesn't matter. What we're going to do is we are going to do the following. we're going to simply say, result is equal to game. We're going to run the game, and we're going to get the result of the game, right? And then I'm going to do the question that I always ask for dictionaries. We're going to count our results. So I'm going to count the results and outcomes, and I'm going to say, okay, have we seen this result before? Has it been an outcome before? If result in outcomes. I'm going to do it in the reverse of the way I did it, but that's fine. So if it's a result I've seen before, great. Outcomes outcomes of that result, right, plus equals 1. I've seen that result once more, right? Makes sense? This is the same thing I was doing on Thursday, only with I've named this outcomes instead of count. Else, if I haven't seen it before, outcomes, result, I put it in, equals 1, right? If I've seen it before, increment the number of times I've seen it by 1. If I have seen it before, I've only seen it once now. And now, rather than printing out the game, what I'm going to do is I'm going to print out outcomes. Now, that's useful-ish, but let's go ahead, but we will render it to make it a bit more easy to read in a minute, okay? So, now for those of you who are asking the age-old question all students ask, okay, Professor Rosen, what do I need to know for midterm 2? This is kind of the form, the generalized form of what you're going to need for midterm 2 for Monte Carlo approximations, if Monte Carlo approximations are on midterm 2. If they're not on midterm 2, I guarantee they're going to be on the exam, on the final exam. Okay? So Monte Carlo approximations, though, are not so bad. It might be something along the lines of, okay, how often do I roll a 7 or higher if I'm rolling 2 6-sided dice, right? Although typically it's a bit more challenging. I think, as you'll see in the practice exam, actually, yeah, we do this. The question I give on the practice exam for this is, how often does somebody end up in jail in Monopoly for speeding? For those of you who haven't played Monopoly before, that's where you roll your 2 dice. Whenever you roll 2 dice in Monopoly and you end up with the same face on them, like you end up with 2 2s or 2 3s or 2 4s, you get an extra turn. But if you do that too many times, you go to jail for speeding. Read the rules. Read the Monopoly rules. If I'm wrong about this, please, then I've been playing this wrong the entire time. But very few people actually sit down and read the Monopoly rules because that game is ruthless and just quick. Unlike most house rules, which add more money into the game and thus prolong the pain. Okay? So you simply ask yourself, okay, how many times do I roll this many times? We'll go over that practice exam when I send it out, because I still have yet to decide on the date. You'll have at least a week's lead time on it. You always will have at least a week's lead time. It will most likely be not this week, nor next week, but the week after. That is probably what it will be. Okay. So, and it again, if I have, and that's all dependent on like whether or not proposal day is. That's what I'm going to sit down and try to figure out tonight. So, but generally what it is your individual kind of outcome, playing the game, and doing this. We're going to go over a lot more fun examples on Thursday, but I wanted to go over this one first because it's fairly easy. We've got these coin flips. So let's go ahead and see what this looks like in a bit more of a nicer outcome. Now, the way I'm going to be printing this and displaying it nicely, that's not something I generally test you on the exam. That's generally something I care about for homeworks. While on an exam, I care about, did you collect the data? Presenting the data is its own thing because that's like an aesthetic thing, and with any kind of data collection or display, it's something where I'm not even sure the best way to display it. So what we're going to do here is we're going to now make this look nice. So so we can understand our results and what we did a bit better. For O in outcomes. So for each of our, actually I'm going to call this sequence in outcome because it is each of these sequences. For each of these sequences, actually, what we're going to do is I'm going to print outcomes, no. Let's do seek, comma, outcomes, that sequence. So in other words, here's this particular sequence, here's how many times I counted it, and then what we'll do also is that I will also print out, no, that's going to do for now, actually. So over here, here's our sequences, right? We had all these sequences. Actually, one of them, we've got one possible sequence missing, by the way, and that's all heads. So we can up the number of trials, by the way. So let's go up the number of trials so we can see that. There we go. So we up the number of trials. Now, this is nice, but it's also like not really sorted, not really collected in any meaningful way, right? It's just a jumble of answers. But it's useful because we can see that the most common outcomes are 5 heads and 5 tails. That's the most common outcome. But it's almost as common is getting 4 of each. And together getting 4 of one or 4 of the other is very common. So let's go ahead and see. Can I do let's go ahead and I'm going to do sorted again, actually, of all things, for sequence sorted outcome. Now, when you sort a dictionary, that is simply sorting the keys. So this just allows me to go over it in a sorted order, and now we can see something over here. So here are our results. We've got all heads, right? We've got all heads, and then we've got 1 tail, 2 tails, 3 tails, 4 tails, 5 tails, all the way to 10 tails. And what we've got here is actually a wonderful distribution, a classical bell curve, as it turns out, actually, where we see that the most common result over here is straight in the middle, and then getting 4 of one and 6 of the other are right over here, 2,000 and 2,000, 1,200 and 1,100, that's close. Why don't we go ahead and actually make this a bit easier to see by putting it in percentages? How do we do that? Well, we have the total number of outcomes, and to turn it into percentage, we just need to turn it into and say that, okay, what's that ratio of? It's the number of times we did this divided by the trials. And so we see here that the chances of you winning that original game that I had posited, flipping 5 heads and 5 tails, right? Okay, is 25%. So 75% house advantage. That's or what is that? A 3-to-1 house advantage, rather. That's a pretty that's a rip-off. Okay. So now what did we do to solve this? How did we figure out this stuff? We could have used statistics and just simply calculated, okay, we could have used the probability of, we could have used probabilities to figure out, okay, what are the probabilities of this, right? Any particular outcome happening is 1 over 2 to the 10th. How many different ways are there to win that? Yes, you had a question? No, not over 1 over 2 to the 10. I'm not sure why I said that. All right. Well, regardless, silly me for saying that. Like I said, been a bit of a day. We've got this. The point being is statistics are annoying. So we aren't going to do the statistics. Instead, we're going to just simply simulate them. So I'm going to leave you with the game that we are going to play when we get back. Okay? The game that we're going to play when we get back. Okay? Is as follows. This one's actually fun. You can play it yourself at home because all it requires is a deck of cards. Okay? Okay, so suppose, so the game we're going to play is a 7-card game. Okay? We're going to have 2 red cards. Okay? And we're going to have 5 black cards. 1, 2, 3, 4, 5. 5 black cards. 2 reds, 5 blacks. We flip them over and shuffle them. Okay, so we don't know which is which. Now the game is, can you flip over 3 black cards without flipping over any red cards? Okay? Now, if I'm playing this in a bar and I am a nasty person who wants to take advantage of people who don't know any statistics, here's what I'll tell you, which is a lie. Well, the first card you flip over, right? You have a 5 in 7 chance of getting that right. 5 in 7, right? There's 5 cards. 2 red cards, 5 and 7. Flip it over. That's right. Now your next card, you've got a 4 in 6 chance of getting that right? Because we've already flipped over a black card. So there's 6 cards left. You've got a 4 in 6 chance of getting that right. And now the last card, right, we flipped over. If you got that right, then we've got 5 cards left. So all we have to do is flip over one more card, and you've got a 3 in 5 chance of getting that right. Now, last I checked, 5 and 7, 4 and 6, 3 and 5, those are all above 50% chance. So I would reckon your overall chances of winning got to be higher than 50%, right? So give that a try on your own and see what those chances end up being. Go ahead and play that on your own and see what the chances are being. We'll come back and we will play that game on Thursday. Last thing I'll leave you with is also, so on Thursday I plan on going over this game. I plan on going over another variation of that game where it's instead a grid of cards, a 3x3 grid of cards, with 2 with 2 red cards somewhere, and you want to get 3 in a row of black cards. Okay. But most importantly, please watch the video on the Monty Hall problem. Okay, please watch that video on the Monty Hall problem before coming to class. That is probably the most important statistics video you're going to be watching for this class. All right, thank you.